Well, thank you all for taking the time to come to my talk on integrating AI and pathology, a novel approach to multiplex IHC data segmentation and classification. So, a few things to disclose. I'm currently a PhD candidate at the University of Toronto, and I'm also Chief Technology Officer and co-founder of Pathology.io, a contract research organization offering image analysis services to academia and pharma alike. And I promise this won't be a sales pitch. So, more often than not, there's an underlying notion that once an individual receives a kidney transplant, they're on the road for recovery if they simply take the medications prescribed to them by their clinician. In reality, multiple complications can arise after receiving the transplanted kidney that can cause it to be rejected. Up to 15% of kidneys will exhibit signs of rejection during the first year of transplant, and if left untreated, can cause a complete rejection. But by identifying the underlying cause of rejection, this can enable clinicians to treat the rejection before it progresses and requires removal of the diseased tissue. So in collaboration with the Mayo Clinic, we received 247 imaging mass cytometry images from 32 archived patient samples bearing a confirmed diagnosis from one of 6 Banff classifications of renal transplant rejection. Our objective was to develop a method to characterize the heterogeneity within and across patients and explore how the spatial dimension can yield a more accurate stratification. Several of the preceding talks have gone over this, but imaging mass cytometry is a multiplex imaging modality capable of imaging over 40 immunohistochemical markers. Tissue sections are stained with a cocktail of heavy metal conjugated antibodies, with each antibody bearing a unique heavy metal tag. These sections are then ablated in a line-by-line manner, and the relative abundance of each metal tag can be used to reconstruct a multiplexed image. Typically, a few square millimeters are ablated from each section, and despite this not being a whole slide imaging modality, it does allow for the sampling of multiple regions from numerous patient samples. In this study, a panel was designed to specifically include markers of immune cells associated with each of the 6 categories of transplant rejection, as well as structural markers of the renal microenvironment. While there are multiple approaches one can take for analyzing high-dimensionality datasets, we opted for a pathologist-in-the-loop approach, meaning any definitions of cell types, renal structures, or patient classifications was done in conjunction with a pathologist proficient in interpreting image features indicative of such classifications. Throughout this presentation, I'll describe the methods behind segmenting and classifying cells and renal structures, as well as deriving spatial features from these classifications. I'll then highlight the various means of data visualization, statistical analysis, and how we use spatial features to gain an improved understanding of differences between disease categories previously undiscovered with non-spatial modalities. It's also worth noting that no proprietary software was used, as this entire workflow is constructed from open source tools. QPath was used for the image analysis portion, whereas Python was used for data processing and visualization. As with most immunohistochemistry analysis workflows, we must first segment cells. We perform cell segmentation using the iridium-193 intercalating agent as our nuclear counterstain, which is functionally similar to DAPI used in immunofluorescence microscopy. Stardust is a machine learning algorithm used extensively in segmenting DAPI stain nuclei. One attribution for its widespread implementation in many digital pathology workflows is the large training dataset used. But since no pre-trained models exist for IMC images, I've been able to transform the iridium channel into a pseudo-DAPI image, enough to enable robust segmentation of our kidney samples. And further developing this as a tool for QPath, I've been able to segment H&E, IF, HDEP, and even Hubble Space Telescope images, as well as offer GPU-accelerated segmentation. So this tool is free to use and available on my GitHub repository as well as the QPath forums. Once cells have been segmented using our adapted Stardust segmentation algorithm, we then set thresholds in conjunction with a pathologist, verifying that our classifications are consistent with what they would manually annotate themselves. Here, we colored in the single positive population for a given marker and left all the negative ones as gray. We then repeat this process for all markers alongside a pathologist for all the markers in the panel, using a representative subset of the images. This in turn creates our composite classifier, effectively assigning every single cell to one or more classes of positivity. So now that we've segmented our cells, we can actually begin to score our samples, grouped by categorical variables such as disease classification. We can quantify the percentage of cells positive for an individual marker and visualize results as a heat map. And while this does allow for the simultaneous visualization of several markers in tandem, we do lose a bit of information regarding their distribution of scores from samples across our population. Consequently, with box plots, we can view individual samples as points and metrics of their distribution, such as the median, interquartile range, and outliers too. Here we show the scores for CD4 memory T cells, defined as being triple positive for CD3, CD4, and CD45RO. But at this stage, we have yet to take into account any aspect of the spatial dimension, such as the spatial localization of cell types to various renal structures. Here, we display the relevant markers for renal structure segmentation, such that a pathologist can annotate their structures of interest. In this study, we were interested in the localization of various immune cells to glomeruli, tubules, arteries, and interstitium. And after obtaining over 3,100 annotations, we then trained a pixel classifier and applied it to all images in the dataset. Several classifiers were explored, varying the type of model, convolutions, feature scales, and markers used. But ultimately, we opted for the model with the highest overall accuracy in a blinded validation set. We then combine our cell classifications and renal localizations such that we now have hundreds of features for each cell relating to marker intensities, cellular subcompartment expression, and renal structure localization. This allows us to profile cell type distributions localized to individual microenvironmental structures. So, much like how lymphocytes infiltrating a tumor mass are more indicative of a cancer patient's prognosis than cell counts alone, the renal localization of immune cells can be indicative of rejection cause. We can apply the same percent positive scoring approach to explore differential localization of various immune markers and immune cell subtypes to glomeruli, arteries, interstitium, and tubules, with a representative image shown above and the structure highlighted in yellow. The main strength of this approach is that it sort of guides cell type discrimination through the eyes of an expert observer, but we'd also like to investigate heterogeneity through an unsupervised clustering approach. So, to get the best of both worlds, we can leverage the cell classifications to annotate cluster names rather than doing this blindly in conventional workflows. So, in this example, we applied phenograph clustering to identify unique clusters across all 900,000 cells of our dataset. Heat maps were then used to visualize differentially expressed features across each cluster, and that's a means of assigning biological meaning to the cluster labels. And while non-spatial single-cell modalities would be restricted to intensity-based features alone, here we can actually view morphological and renal localization features as well. Furthermore, we can view the prevalence of clusters across different disease classifications. Now, when projecting clusters on a t-SNE plot, it becomes somewhat challenging to discern unique populations given the vast number of cells. However, we can perform the same method using renal localization and disease classification to stratify samples and explore cluster proportions within them. So for each renal structure and disease category, the proportions of the most predominant clusters were shown. Each stacked bar corresponds to an individual image, with the height of the segment corresponding to the proportion of that cell type. This is one parallel approach to our percent positive scoring that leverages pathology supervised classifications to score samples for different cell types. We can also query our dataset for the ID of specific images exhibiting high proportions of specific clusters, showing markers differentially expressed in them relative to others. But even at this stage, we have yet to extract all the spatial features that we can from this dataset, nor have we actually demonstrated the value over non-spatial features. So we can generate spatial features such as annotation distances, the distance of each cell to the nearest renal structure, cell distances, the distance of each cell to the nearest positive cell type, and Delaunay triangulation, identifying spatially grouped clusters of cells sharing markers in common. And while it's great that we can generate these features, we also need to explore the practical applications of spatial feature augmentation. So intuitively, one practical application we wanted to investigate of our spatially augmented cells was the ability to predict patients' cause of transplant rejection. Our intent was not so much to compete with the existing diagnostic standards of care, but rather train a classifier to predict the patient's rejection category and identify which spatial features played the most important role. I had to settle on a choice model to use for training the classifier, so XGBoost, given that it's a gradient boosted decision tree designed for speed and performance, and also has excellent support for Python's NumPy arrays and GPU accelerated learning, was ultimately my top choice. Cellular features in our IMC dataset were extracted and used to train such a model. The key predictors would be categorical variables such as the cause of transplant rejection. Now, once the model has been trained, the variable importance of each feature, so in this case cellular features, can be obtained. Variables with a high importance are drivers of categorical prediction and can significantly impact the accuracy of the classifier. So, how do we go about training the classifier? Well, let's use a hypothetical demo of two patients with a BK and ACR diagnosis as an example. Well, first we must assign each cell to the ground truth classification. It's reasonable to conclude that for a patient with an ACR rejection diagnosis, all images taken from that ACR patient are of ACR classifications, and all cells derived from all images from an ACR patient are also ACR, and vice versa for BK. This property is essentially appended to our per cell measurements as a categorical column. We can then perform a train test split and begin training our cellular classifier. After prediction, you can see that cells are being classified as either ACR or BK, but how do we traverse up the hierarchy back to the patient level? And the answer to this is mode consolidation, also known as majority rules. Now, for each image from a patient, we assign the classification based on the most commonly represented cellular classification. And going one step up, we can predict the patient classification by the most commonly represented cell classification. Putting this all together, we essentially have a framework for predicting categorical labels from supplementary sample categories. And this isn't just limited to kidney transplant rejection categories. This can also be applied to any feature of the dataset in which comparisons across one or more groups is needed, such as differentiating a control from experimental treatment category. But now begins the fun part, profiling the feature importance from our model to identify the most valuable features and the markers that they're associated with. So first, we calculate the cumulative importance of all features bin by the marker that they're derived from. This indicates which markers play the most important role for the classification at the cellular level. Next, we then subdivide these features based on whether or not they were spatially dependent or not. Nearly 100% of the time, the model would rank the spatially derived features higher than the non-spatial ones. Still, we were curious to compare our model's performance with and without the use of spatial features. So now that we have the variable importance for each feature and the marker that it was derived from, what if we iteratively train the model to predict rejection category at the cellular scale one at a time, or feeding in all the features derived from a marker one at a time? In blue, we show the model's performance when we trained it using non-spatial features, and in orange, we show the accuracy when we add spatial features. When we include only CD11C and all the features associated with it, we see that spatial features yields a considerably higher accuracy than using non-spatial features alone, effectively a free improvement in accuracy without having to include another marker in the panel. When we include collagen, in addition to the previous, the maximum accuracy jumps up from 45 to jumps up to 45%, and almost 53% when including CD45RA. And while these accuracies seem low, it's important to note that these are shown on the cellular scale. All cumulative features, quite a tongue twister, applied to the patient level yields an accuracy of about 84%, or 21 out of 25 correctly predicted samples. Not only does this tell us which markers play the most important role in predicting disease category, but we also see how inclusion of spatial features improves model accuracy at no cost. Much like we had done with the percent positive scoring heat maps, we can visualize the most valuable features for the classifier, grouped by rejection category. But as previously mentioned, heat maps lack the ability to portray population distributions, and when visualized as a violin plot, we can actually truly appreciate the heterogeneity in feature expression across these disease types. This essentially indicates that it's not always one feature actively differentiating a disease, but rather multiple in tandem. But as the old saying goes, seeing is believing. Here we randomly sampled 40 regions across our samples with the uric adherent channel shown alongside the DNA counterstain. Next, we show an overlay of non-spatial features, unique adherent intensity across our cell. And you can see that there is some variation across our samples. But if we visualize the fifth most important feature in our model, a greater degree of inter- and intra-sample heterogeneity can be seen. But how does this actually fare in practice when trying to resolve two similar disease categories? Well, historically, chronic and acute antibody-mediated rejection had been a challenge to differentiate. And while variable expression of weak adherent has been observed in the past, the difference here is quite minor. But when viewing our fifth most important feature, there is quite a stark contrast in feature expression. That being said, this is just one of the many features working in tandem to differentiate chronic from acute antibody-mediated rejection, as well as other disease types. The takeaway message here is that analysis tools that incorporate spatial proximity and localization reveal novel forms of intra- and inter-microenvironmental heterogeneity. So in short, we've introduced an open source pathologist-in-the-loop workflow for the quantitative assessment of microenvironmental heterogeneity. The utility of this method was demonstrated on a dataset of about 32 patients encompassing 247 high-dimensionality histopathology images, containing a total of about 900,000 cells. And our workflow provides a robust and automated approach for analyzing large multiplex datasets, facilitating the identification of biologically and diagnostically relevant interactions within the tumor microenvironment. And on that note, there are several people I'd want to thank: Dr. Trevor McGee, my supervisor, Dr. Bradley Waters, but the real unsung heroes are actually the QPath community. I started out in the field of digital pathology with next to no experience whatsoever. In fact, I had no programming experience until I ended up joining a computational core. Thankfully, the wonderful and active QPath community was, there for me and able to answer all the questions I had. And, in return, I try and be an active forum member as well. So if you do have any challenges with using QPath, whether it be something as basic as simple HDAB analysis or more complex multiplex analysis, by all means, post a question on the forums and I'll try my best to get back at you, or back to you. Yeah. So on that note, I'm happy to take any questions, comments, or concerns.